Today we're out in a woodlot to collect soil samples and look at a soil profile. So I've cleared a small spot here and I'm going to stick my probe in and lay it out on the board. Now I'm going to go back down the same hole because my probe only goes so deep each time. And I'll go down a third time. Apparently that's as deep as I can go. This is the soil sample as it was extracted from the ground, and you can see a couple of interesting things here. You can see that the soil has layers. And so if I start with a knife up at the top and go down, you can see there's a color change about there at 10 centimeters. There's another color change at about 22 centimeters. This is some topsoil that fell in the hole after I took my probe out. But you can see another color change down here at about 45, 46 centimeters deep. Okay, so we have three horizons in this case, actually four horizons. We have an AH, we have an AE here, we have a B of some sort, probably a BF, and we have parent material, C horizon. This here, again, is soil that fell down the hole after the second probe. Okay, but this lighter colored material is the parent material. So we have three different soil horizons in this particular case. We have four different soil horizons. We have an AH, we have an AE, we have a B, probably a BF, and we have a C horizon. So we have four soils horizons. This particular soil is approximately 70 centimeters deep. It's a well-drained soil. The way we know that is because we have bright reds and yellows in the soil. And so it's a well-drained soil in a woodlot at the University of Guelph Ridgetown campus. To show how quickly a soil can change, we're going to move from this well-drained area to a poorly drained area. And I'll keep the camera rolling just so that you can see how close these two spaces are. I will be walking. So, as we walk along, I'll talk a little bit about the area that we're in. We are on the Ridgetown campus of the University of Guelph. We have approximately an 8.5 acre woodlot on this campus. And so we are heading in that woodlot from a higher, well-drained area that has lots of sand in it to an area that is more poorly drained and has a lot more clay. And you can see that it's not going to take me very long to get there. Matter of fact, we're getting pretty close already. I got to keep looking down or else I'll fall down. So the woodlot itself is relatively small, only 8.5 acres, like I said, and we have several different biotypes or ecological zones within this particular woodlot. Okay, so here we are. We've made it to the poorly drained area, And you can see that did not take very long at all. All set up, and we'll take a look at the soil on this particular site. As I did at the last site, I'm going to have to go down the same hole 2 or 3 times in order to get a whole soil profile. So let's start. You can probably tell already that this soil is quite a bit different than the first one. This is a poorly drained soil profile, and when we look at it, it's relatively difficult to separate the different horizons in this particular soil. So if I move my knife from the top and I stop at the bottom of the A horizon, the bottom of the A horizon is approximately 20 centimeters deep, and the boundary between the A and the B horizon is relatively indistinct. It's difficult to really tell where the boundary is. Okay, so the B horizon would start at about 20 centimeters deep and go down to approximately here, which is 53 centimeters deep, give or take. And so in this case, we only have 3 horizons. We have an A horizon, an AH horizon. We have a B, which is a BG horizon, and we have a CG horizon. Now the reason why we have the G after the B and the C is because the G stands for glide. Glide means that the soil is poorly drained, and so we get these very dull gray colors. But if you look closely, there are some brighter specks of yellow and red within the dull gray background. That's called glying, and it's an indication of poor drainage in a soil. This is the area that I took the poorly drained sample from, and you can see by as I pan the camera across, you can see that the vegetation here is mostly maple trees and the area is fairly flat. If I pan down, we can see that the soil looks like there's been water standing here, and there has been water standing here in the spring. This is the area that I took the well-drained soil sample from. You can see that there are a lot of maple trees here, but there are also other species as well. There is a lot of black cherry, as well as some maple trees. So it's similar. The maple trees are similar. They are adapted to both well-drained and poorly drained areas. However, the black cherry does not grow in the low-lying areas, the wet areas, because they are not adapted to wet conditions. Water does not lie on the surface here because it is the top of a knoll, and water drains fairly easily, flows fairly easily across the surface. And in this case, the soil is sandy, and so it flows through the soil very easily, so water does not stand in this particular area. It drains away very rapidly.